Jai Hind to all. Today I am here to present the video lecture on the subject control system, subject code BEC 602. I am Dr. Amit Garg, Associate Professor in ECE Department of Akgec Garg Engineering College. And the topic that I have chosen is block diagram reduction. So, why I have chosen this topic? Because, if you will see the plants or the actual industry, plants in the industry, then those plants you can say are made of various subsystems. Okay, so whenever each of the subsystem we will consider, then it will make a complete system, and each of the subsystem will be represented by its respective gain, or you can say you can say these subsystems are arranged in a manner so that we are getting the output. Okay, so how a complicated system in which there are various subsystems are connected together, how can we obtain the overall transfer function for that type of system? Okay, so block diagram reduction. In any complex real-time system, many individual subsystems exist. Okay, and these subsystems can be represented by means of individual blocks. Okay, so by individual blocks, and each and every block is having the transfer function. The individual blocks of each subsystems are combined to form the block diagram for the system. As I have already told, the block diagram constitutes basically when we are arranging the various blocks of a system, wherein each block represents a subsystem having some transfer function value. Okay, like this. So these are, you can say this is a subsystem wherein we are applying some input, to the system, and we are obtaining output at the system, wherein various subsystems like 3 subsystems are arranged here. Okay. So these individual blocks contain the transfer function of each subsystem. You can see here, block diagram reduction is a technique used to simplify complex block diagram in control system, making them easier to analyze and understand. Okay, so for better way of analyzation, we have to reduce the block diagrams. It involves using rules and techniques to combine blocks, rearrange elements, and eliminate feedback loops to find the overall transfer function of the system. Means if we have to reduce the block diagram, then what we have to do? For a complex block, we will have some specific rules. By using those rules and by eliminating the feedback loops that are existing in the system, we can obtain the overall transfer function of the system. Okay. So like before going through the reduction part, first of all, we see the various elements that are present in a system. Okay. So first one is the summing point. You can see this is the block diagram where this GS is forward path gain, this HS is feedback path gain, and the element which is covered by this dotted rectangle is basically a summing point. Okay, so summing point is a point where two or more signals are either added or subtracted, is known as the summing point. Okay, so you can see this is the summing point. And you can see here RS input is given to this plus sign, and we are having this feedback signal coming from here with negative sign. Okay, so this ES, you can say ES in this case, which is the signal coming over here, is nothing but RS input minus BS. BS is the signal over here. Okay, and you can see this BS is nothing but this is CS into HS. So BS is CS into HS. Okay, so that's why how we will calculate this error signal. And if you will see the relation between CS and ES, then CS equals to ES into GS. So one type of point is this. Another important point that we have to consider in case of block diagram reduction is takeoff point. Okay, so you can see again the same diagram is here. Again the same diagram is there. You can see this point is basically your takeoff point. You can see from this point there are two branches connected. So the point at which a signal is applied to two or more blocks, you can see from this point, you can see input is coming from here and input is going in this particular direction. Okay. So the point at which a signal is applied to two or more blocks is known as the takeoff point. The signal might either be an input signal or an output signal. Okay, so this takeoff point is shown here by the dotted lines. Okay. Now we will see the various rules that are used basically for block diagram reduction. Okay. So these are these are some standard rules that we have to follow while reducing our block diagram. Okay. So you can see here there are two summing points connected, and you see that here input is A, here input is B. You are getting A minus B at this plus point, and when we are adding this, so we are getting the output A minus B plus C. Similarly, if you are rearranging these blocks, if you have put this block here and this block here, then you can see here again you are getting the same output. It means it will follow the law of associative law. Okay. And another example is this, you are getting the output A minus B plus C, and similarly you are having the output A minus B plus C. So this is you can say it follows the principle of it follows the associative law. Now blocks in series or combining blocks in cascade, like this you can say blocks are connected here in series. So the overall output is A multiplied by G1 into G2. So this is A G1 G2 will get at the output, and so that this G1 and G2 can be combined to make a single block having transfer function G1 G2. So you can see this A times G1 G2, you are getting A times G1 G2. So if there is a situation like this, we can combine these two obtain like this. Then third one in blocks in parallel. So you can see here one forward path is this. Forward path is the path wherein signal is flowing from input towards output. So you can see in both the cases signal is flowing from input to output side. So you can see here the both here at the summing point both are plus sign. So the output is nothing but A times G1 plus A times G2, that is A times G1 plus G2. So you can represent this by a single block of transfer function G1 plus G2. So that's why you are getting the same output. So it means whenever blocks are connected in parallel, you can simply add up their transfer function to obtain the overall transfer function. Now the rules related with shifting of summing points or takeoff points. Okay, so here the rule is shifting summing point behind the block. So this is your summing point. What we are doing basically, we are shifting this summing point behind this block. So important thing is that whenever we are shifting the block beyond behind the block, whenever we are shifting summing point behind the block, then the feedback path associated with that block with that summing point is get multiplied by the transfer function of the block beyond before which we are placing our summing point. Okay, so you can see here when this summing point moves over here, then this is multiplied by, you can say, 1 by G. Okay. So whenever this thing happen, then you will have to multiply by 1 by G here. Okay. So that you will get the same output, AG minus 1 by G times B, and output is here AG minus B. Similarly, shifting summing point beyond the block. So if we are moving this block from here to here, then you can say we are multiplying by this block transmittance block G. Previously we have divided by 1 by G, but here previously we have multiplied by 1 by G, but this time we will multiply by G. So again you are getting the same thing. Now for shifting the takeoff point behind the block, so this is your block and you are moving this point behind the block. So what happened if you are doing this, then this basically here you can see the unity feedback is connected, unity gain is connected, so it will get multiplied by G. So you can see this thing. Okay, so again you are getting the same output and shifting a takeoff point beyond the block. So if we are shifting this takeoff point beyond the block, then what happened, this feedback path will get divided by 1 by G. So, you can see you are again getting the same thing. And shifting takeoff point after summing point. So, this is the another rule. Generally, we are trying to avoid this particular rule because in this case there will be more complexity arises. So, you can see here rather than this is a single summing point, you are having two summing points. Okay. So, you can see in both the cases we are getting the same type of output. Here again we are getting the output A minus B, A minus B, A minus B, A minus B. So, this is the combination when we are shifting the takeoff point when we are shifting the takeoff point after the summing point. Okay. So, these are the rules. Other rules, shifting takeoff point before summing point. Again we can see it is a complicated type of thing that we have obtained. Single summing point will be converted into two summing points, and you can see the output again will become same. Now, removing minor feedback loop. So, the formula for this is simply B by A. If you will calculate B by A here in this case, so it will become forward path gain upon 1 plus forward path gain multiplied by feedback path gain. So, this can be easily eliminated. When plus minus is given, then this sign is plus, and if here plus sign is given, then we are getting the output G upon 1 minus GH. So, this is how we can eliminate the minor feedback loop. Okay. Now, removing block in forward path. So, you can see there are these are two forward paths and they are connecting with a summing point. Okay. They are connecting with a summing point. So, you can write it like A times G1 plus G2. You can combine these two blocks in parallel also, or you can also do this. You are shifting this block to here. So, it will become G2 by G, and then you will add it up and again you will get the same thing. So, these are basically the rules that we have to follow for block diagram reduction technique. Okay. So, every time whenever you will solve a particular problem, either of these rules may be applied. It is possible maybe you are using one rule or a combination of rules. Okay. And you will get the block diagram reduction done. Okay. So, now let us see some of the problems associated with it, and like first problem. Okay. So, you can see this is one summing point, this is another summing point, this is third summing point, and we are having forward path gains G1s, G2s and G3s, and feedback path gain H1s and H2s. Now, we have to obtain the CS by RS or overall transfer function of the given system. Okay. So, now how can we solve this particular problem? Important thing is that whenever you will going to reduce a system, there may be minimum one, or maybe there may be a possibility that you are having one or more techniques available. Okay, but generally we will follow that technique which will basically which is the optimum manner for the reduction of the block diagram. Okay, by which we have to apply minimum number of rules to get the overall transfer function to get for the overall transfer function. Okay, like here in this case, you can see first of all from here we can see these two block diagrams. These two blocks are connected in parallel. So, it is very easy to connect them in parallel to eliminate this summing point. Okay. So, you can see first of all we are taking these two blocks. These two blocks are connected in parallel. Okay. So, eliminate G2 and G3 connected with summing point. So, whenever you are solving the question, you should write these steps in between. Okay. So, what happened? You can see here G3 is connected with plus and G2 is connected with minus. So, it will become G3s minus G2s. So, now your block diagram is reduced like this one, means this dotted line block will be reduced in a single block, with transfer function G3s minus G2s. Now another thing what we can do, can we shift this summing point from here to here? Important thing is that here signal is transferring in this direction. So what we are doing basically, we are shifting our summing point beyond the summing point after this block H2. Okay. So what happened? The feedback path associated with this block will get multiplied with the transfer function of this block. Okay. So you can see here, these two blocks also connected in series or in cascade. So you can also combine them to obtain the overall transfer function. This will come G1s into G3s minus G2s. And another important thing is that when we have shifted this summing point from here to here, then this block H1s and H2s are in series or in cascade. Okay. So we can simply make it like this. And now this summing point comes over here, and I told you the feedback that is associated with it is having unity gain. So it will get multiplied by H2s. So you can see that this is the situation. So this is the situation after eliminating this forward path and shifting the summing point after the block H2. Why I am saying after the block H2? Because signal is traversing in this direction only. Okay, that's why I am saying that it is that we are moving the summing point after the block H2. Okay. Now you can easily reduce it. Again, this and this are come in series. So this is G1s into G3s minus G1s into G2s. And again here these two are in cascade. So it will become H1s into H2s. And this is the summing point. Okay. So now come to the next part. Now what we can do? We can simply combine this summing point and this summing point and make a separate loop and make these two loops separately. Okay. So you can see when we are removing this minus sign, we are multiplying by a minus 1, multiplying by a block of minus 1. Or you can also do this thing whenever you are moving in this direction. So this is minus sign and this is minus sign. So you can make it positive also. Or you can place a minus 1 block with minus sign. So it will just change the sign of this. So you cannot directly do it also. Okay. And this you can see here, it is positive and again it will become negative. So you can see this is with the negative sign. Okay. So now these two blocks you can easily solve separately. So this is minus H2s and this is also minus. So 1 minus of H2s will become 1 plus H2s. Okay. And here you can see that this is your forward part transfer function and this is your feedback part transfer function, and your feedback is basically negative. Okay. So G upon 1 plus G into H. Okay. So you can see this, this will be the, how you are solving this. Let us suppose this whole is, let's say, G5 and this is, let's say, H5. So how you will solve it? G5 upon 1 plus G5 into H5. When you will solve this, where G5 is this value and H5 is this value. So you will get this value. Okay. Now simply these two blocks are in series or in cascade. So you will multiply these two blocks simply to get the output or overall transfer function of the given system. So CS by RS is this one multiplied by this upon this. So this is basically the overall transfer function for the given system. Okay. So let us take another example. Here for the block diagonal system shown in figure, determine the transfer function using the block diagonal descent technique when the input RS at any instant of time is applied to one station. Okay. So here you can see there are two stations. So what they are saying that at a time we are applying only one input. Okay. We are only one input. Okay. So let us suppose input is applied first here and then we will apply it over there. So in the initial instant, if we will see what we have to do, because these systems are linear systems. So, these systems follow the principle of superposition. So, in case of principle of superposition, what you can do? You can take one input at a time and get the output of according to that input, and then you will take another input and get output according to that, and then you will combine those two outputs to get the overall output of the system. Okay. So, what we will do basically, first case, input RS is applied to station 1 only. Okay. So, in this case, you can see here, this station 2 is not there. So, what is the role of this summing point? The role of this summing point is to add some signal over here. But if this signal is not there, then there is no use of this summing point. So, we can eliminate it. Okay. So, that is why you can see here it is eliminated in this diagram. Okay. So, we are applying input RS to station 1 only, and this is the same block diagram. Okay. Now, what we are doing basically, you can see from here, we are shifting this takeoff point after this block. So, whenever you are shifting the takeoff point after the block, then what happened? The feedback path associated with this takeoff point will get divided by the transfer function of this block. Okay. So, that is why divide, or you can say multiply by 1 by G3. So, you can see that this we have written as H3S into 1 by G3S. Okay. And another things will remain same for this particular step. Okay. So, after summing point, G3S will be there, H2S will be there, and H1S will be there, G1S will be there, and all the things will be there. Okay. Now, how can we solve it? You can easily solve it. You can see this particular block. Okay. In this particular block, you can see there is a forward path gain G3 and feedback path gain H2. So, you can eliminate it by G3 upon 1 plus G3 H2, and again after eliminating, you can see G2 is in cascade. So, you can write like G2 G3 upon 1 plus G2 G3 1 plus G3 H2. Okay. So, in next step, we have eliminated this feedback and that series path, and you can see here this will come into the feedback. So, this is again coming here. Okay. And this H1S will remain same, and G1S will remain same. Okay. So, now you can see here, this is the forward path and this is the feedback path with gain minus. Okay. So, when it will become minus, then your you will get the positive value. So, what we will do? We will basically eliminate this feedback path loop, and then we will multiply it with G1S, and these two will become in series, and we will get the overall transfer function here, and then H1S is with the feedback, H1S with the feedback with this overall transfer function. Okay. So, in the next step, we can see that we have done this, we have solved this, eliminated this feedback path, and then we can multiply it. So, in the next step, you can see that it gets multiplied. Okay, it gets multiplied, and then you can see this is the simple feedback loop where forward path gain is this and feedback path gain is this, and feedback is minus. Okay. So, you can easily solve this. Okay. So, G upon 1 plus GH. Okay. So, G is this completely, and upon 1 plus G into H, then you will solve it. So, you are getting this. Therefore, this output we are assuming at C1S because we are applying input only at RS. So, C1 by S by RS will become this. Okay. Now, if we are applying input RS to station 2 only, so in case of station 2, we are applying it over here, and because we are not applying any input over here, so there is no requirement of this summing point, only this minus sign will come over here. Okay. So, you can see this, we have done this, we are now applying input over here. Okay. So, this is the situation. Now, what we are doing, this negative sign we have taken here. So, it will become minus H1S. Okay. And now, what we are doing, basically what we are doing, we are we are shifting this summing point before this block G2. Before this block G2, so when we are shifting this block before G2, then you can see the gain is H2S. So it will get multiplied by 1 by G2S or divided by G2S. So this is the situation here. And you can see this is at this summing point, this will be in series. So it will become minus G1S, H1S, and this H3S comes in the feedback. Okay. So this is the modified block diagram after doing that. Okay. Now what we will do, basically we can eliminate this feedback path loop. So it will become G2S upon 1 plus G2S H3S, and this is RS, this is G3S, and you can see at this feedback point, you can see this signal is coming in same direction. So this is minus G1 SHS and this is H2S by GS. So these two are in parallel basically. Okay. So what is the output? Minus G1S, H1S minus H2S upon GS. And this is the situation. Now here you can see simply how we will solve it. You can see here we are providing the input and getting the output over here. Okay. So this is the forward path gain, and what about the feedback path? We are moving in this direction. This whole become the feedback path, and you can see this block and this block comes in the cascade. Okay. So you will get multiplied this. So you can see this multiply by this, and this is the feedback. Okay. So when you will solve it, you can see next step we can make it like this. You can see the calculation easily, and then you can apply this G3S is in forward path gain, and this is in feedback path gain. Okay. So that's why you will getting the output C2S by RS this time. Okay. Means RS applied at station 2, we are having the output. Now we can obtain the overall output if we will add simply C1 plus C2. So, okay, so in that case RS will be multiplied here from this and here from this, and then you can add it up. Okay. So these are basically the references that I have taken for preparation of this presentation, and thank you so much.